All right, so today's lecture is about sound. I got my new background in honor of the new topic. So but prior to getting into sound, talking about sound waves, we do need to wrap up a few things about energy and waves from last week's I guess Wednesday's lecture. So I want to turn on my tablet here and give you some notes about that. Okay. All right. So first, let's see. Let me cut that again. First, wrap up energy and waves. And I have some demos I want to show you too. Okay, so the first one is, so computing total energy. So the idea is that to calculate the energy, what you would do is sort of add up the differential amount of energy. Like the energy stored in every little segment. And so like the idea is that we have an expression for energy per unit length, right? In the string where there's potential energy or kinetic energy per unit length. And so the idea is that you kind of think of each little bit of length having a little bit of energy in it, and it varies, from place to place because the configuration of the string or whatever varies from place to place. And so to get the total energy, you would have to just add it up. And so that's, in the case of a continuously varying function, that can be done by doing an integral. So I'm gonna kind of then see what this is. This would be like dk plus du. And then the idea is that we actually have kinetic energy and potential energy per unit length. And which is nice because that kind of allows us to do this integral with just one integration variable, x. And then I can kind of actually write this with their two expressions. We got 1/2 mu, and remember it's the particle velocity squared. And the second expression was 1/2 the tension times the particle, or I guess it basically the slope, right? Squared. All right, now, so that's kind of essentially like the computation. Now, anytime you do an integral, you're going to need to sort of define your limits. And so the limits are going to, in a sense, then depend a little bit on what the problem's like. If we're talking about like a harmonic wave or something like that, then often they'll be talking about the energy over one wavelength. Because if you think about it, a harmonic wave just goes on and on forever, and the total energy would be infinite in the sense that, if it goes on forever, it has to be like on an infinite string. And so it would, this computation is going to give you infinity. So to make it finite, I usually talk about things like like the energy in one wavelength, or the energy, in two wavelengths or something like that, but or the energy in like 3 centimeters, or something like that. But they'll give you a finite thing, and so so you kind of let that dictate your limits. So that's for a harmonic or a continuous wave, one that kind of spreads across a presumably or at least a string that's modeled as infinitely long. Now, on the other hand, though, if you're talking about a wave pulses are typically, sort of localized little disturbances, and far away from where it's localized, there's no disturbance. And so in a sense, for those, you just really have to integrate over the area where it's disturbed. But since the disturbance kind of goes to zero, like right way in front of it or way behind it, that would mean that these functions, like the particle velocity and the slope, would also sort of go to zero far away from it. And so in a sense, for a pulse type function, it's often convenient to have the limits just go from like minus infinity to infinity. Like you imagine there's a pulse on an infinitely long string. And then the idea is like, well, of course it's not really infinitely long. Maybe it's only a couple of meters, but since maybe the thing's at the center and 1 meter away on the side, it's pretty much zero. And so the idea is if you go from that 1 meter all the way to infinity and just adding a bunch of zeros, not really adding anything to your calculation. And oftentimes for a localized wave pulse, the wave functions are going to be sort of difficult functions to integrate, especially if you want to find an indefinite integral. It's always better to find a definite integral, and then oftentimes they simplify better if that definite integral is like an improper integral, right? Those are the kind where the limits are infinity. So so if we're like so the limits in the case of like a pulse wave, you typically would take them to be minus infinity to infinity. You're making you're sort of making an approximation, but but it's not going to introduce any error really. So it's zero over there anyhow. All right, so just a little aside, a note on the limits. I could have wrote something down, but it's just kind of long. I'm going to kind of keep moving though. So let me do as a sort of an example. A traveling harmonic wave. You could say Sy of x and t is equal to a cosine kx minus omega t. So it's like traveling in the positive direction. I can calculate the particle velocity by taking the time derivative. The derivative of the cosine function will give you a minus sign, but the chain rule is also going to give you a minus omega. So I'll have a minus omega a sine. I'm sorry, there's two minuses, so there's really just going to be plus. So go erase your function. There it is. Kx minus omega t. And then the slope, so your derivative of cosine is going to give you a minus sign. The chain rule in this case will give you a plus k. So I'm going to have minus k a cosine kx minus omega t. So if I just kind of wrote this whole thing out, the energy, and just kind of fill in these into the thing I had above there, I can, yeah, so it's like 1/2 the linear density, and then I'd have a squared omega squared cosine. I'm sorry, sine, isn't it? Sine squared kx minus omega t. And then I got plus. So the second one is like the potential energy is 1/2 attention. And it's supposed to be the slope squared. So I square this, I'm going to have a squared k squared. And I have cosine, sorry, sine squared. No, I made a mistake over there. Yeah, like dx. Yeah, my mistake is over here. I took the derivative of cosine. I should have got sine. Let me erase that in here. Deep. Okay. Sine. Yeah. All right. So, so here's like the first thing, and I actually pointed this out, I think, when we were first talking about energy. And the idea is that even though these terms look different, they're actually exactly the same terms. And I can kind of show that because if you recall, right, omega divided by k is equal to the wave speed. And so like omega squared, you could say is equal to k squared v. But V squared. But V squared is equal to the tension divided by the linear density. So what that means is that omega squared is actually equal to K squared F over mu. And you can see that if I put that in for omega here, that what would happen is that would end up these terms right here, all these terms right here, would end up being exactly the same as all these terms right here. So if those are the same, then I could just combine the terms because they both have this sine squared stuff. You know, does that make sense? And so, yeah. So the energy, the kinetic energy, the kinetic energy, the potential energy is equal at all points on the string or whatever. And so, it really amounts to just choosing, just choosing to calculate one or the other. The way I've done this, like this substitution or like with this process here, it kind of makes sense. Just put it in here, and what would basically happen is you get something like this: E is equal to integral, and like since they're exactly the same, you can kind of just add them up, and 1/2 goes away, and I get F A squared K squared sine squared Kx minus omega t dx. Now, there's a couple of like other things I want to point out here. Energy is basically conserved. Try that harmonically. Okay, I could also kind of, let's see. I could go from 0 to like lambda or something like that. So this is would be the energy, the total energy in one wavelength. Now, it might be strange because you think, well, what's lambda? Of course, lambda is related to K. I could say that Kx is equal to 2 pi x over lambda, because K is 2 pi over lambda. And in that sense, you could kind of see, well, when x is equal to lambda, I guess, I guess you could also say that if x is equal to lambda, then x is equal to 2 pi over K, right? So in a sense, you could have your limits be like from 0 to 2 pi over K or something like that. But you might think, okay, if I'm gonna do this integral, there's ways to do this integral. The simplest way to do this integral is actually just to realize that anytime you're integrating over across the sine squared function, the result is going to be, if you go over a certain number of wavelengths, or like which we are exactly doing, the result of this integral is just going to be half of the integration range. So I could just kind of replace the whole thing and say that the energy is F A squared K squared, and then times 1/2 lambda. And then of course 1/2 lambda, you could say is like K over pi, or pi over K, I guess. So, I mean, in a sense, that becomes your answer. That's how much energy there is in one wavelength of a traveling wave. That's the total energy, and it's in terms of the tension and the wave number. If you're actually given like physical dimensions, like the length of it, or the length of one, or the actual wavelength, or something like that, then you could put it in terms of lambda instead. If you're given the linear density, then you probably also have to be like given the wave speed, or maybe the frequency, so that you can get the wave speed. Because if this was written in terms of linear density, I think if I instead chose to put everything in terms of the kinetic energy, then the linear density would be useful, but then I also need to know omega, and so yeah, so I think you know, this is, in this example, I'm presuming that we know the tension, right? All right. Okay, so let me, yeah, so let me, I guess maybe let's take a pause here. I'm gonna show this. I'm gonna show this little demo I have. All right, so share demo screen. Okay, so this here, you guys can see this, right? What we're seeing here is on the top here, this is y as a function of x, and so this is the particle displacement. And what I did is I made it like a string, but the string is like composed of like little segments. And you can look at each little segment, just goes up and down, right? That's what they had of a transverse wave. That the displacements are perpendicular to the direction of propagation. You can see the propagation is here, like I'm following the top of the or the crest of the wave with my mouse. That's the propagation going to the right. And there's a kind of a color coding on here, but the only coding, or the only color you see is purple. And but the purple consists of, you know, blue and red, right? And the idea is that these graphs down here, this is the potential energy per unit length, and this is the kinetic energy per unit length. And you can see they're exactly the same, like where the peaks of the potential energy are also the peaks of the kinetic energy. And then the bottom graph is the total energy. So the total energy consists of kinetic plus potential. I add it together and I get, you know, it's purple. And so the idea is that, of course, since they're the exact same, you know, sort of, they peak at the same places and all that stuff, the total energy is going to peak at the same places too, it'd just be twice as tall. And then if you kind of look and compare it to the displacement of the string, you can see that the points where these are peaking, like right, you know, like here, it corresponds at the same time to the points where the string is basically crossing through the origin. The points where you have zero potential energy and zero kinetic energy and zero you know, total energy, those are the points at the crests and the troughs. Because at the crests and the troughs, remember, there's no kinetic energy because the little pieces of string are reaching the top and they're sort of stopping. So they get up here, they stop, and then they kind of go down. And so since they reverse direction, there's an instant time where they are not moving, and they're not moving, there's no kinetic energy. But you might wonder, well, wait a minute, like in a spring, when something's fully displaced, that means it has the most potential energy, right? Because the spring is stretched the most. But the thing is, at that location on the string, right here, as the peak crosses where the mouse is here, you can kind of see the adjacent pieces of string are not really pulled far apart from each other. So there's no real stretching of the string at those locations. So there's no potential energy at those locations. The potential energy is actually at the same locations where you have the maximum speed. At these points, like this point now, right there, or right now, that's when the thing's moving by and moving by at the fastest speed. So it has the most kinetic energy, but also when you look at it and you look at the adjacent pieces, you can see they're most stretched out, you know, because they're furthest apart. And so that's what also has the most potential. So that's why, you know, like you know, you can kind of see in the picture here, that's why the kinetic and the potential energy in a traveling wave is equal at all locations at all times. And you can see that you know, there's no place on this string where it's just red or just blue. It's always, you know, exactly purple, just various shades of purple. And the deeper the shade, the more energy, the lighter the shade, the less energy. But the idea is that it's always purple. It's all equal amounts, and so they add up to purple. Right, now, I'm going to contrast that with a standing wave. And so let me kind of go back to the notepad. And the graphic's pretty helpful, right? You guys think? I mean, let's see here. Okay, I gotta do this. All right, so yeah, it's good. It's a good visual. You know, I programmed that thing. All right, but you know, it's Flash, so it's obsolete already. But it was Steve Jobs who killed Flash. You know? I didn't know he was going to do that. All right, now I'm going to go back to the notepad. Yeah. All right. So, so let's look at standing waves, right? all right, so like the energy in a standing wave. So first write the wave function, Sy of x and t. And I want to, like, in the last lecture, there was like a 2 here when I talked about a standing wave, but I don't want to have a 2. And then also, I think I might have had like cosine, cosine. I'm going to have sine, sine this time. Sine kx, sine omega t. The reason I want to do sine, sine is because it really doesn't matter. All that, remember, sine and cosine are essentially the same kind of functions. There's just like a shift. And so this one, at t equals 0, there'd be like 0 amplitude everywhere. And at x equals 0, there'd be 0 amplitude at all times. So x equals 0 represent a node, and t equals 0 represents like 0 displacement of everywhere at time t equals 0. If I use cosine cosine, then x equals 0 would represent an antinode, and t equals 0 would represent like the full full displacement. It doesn't really exactly matter because once time and position start being varying, it still looks the same. I guess the effect of sine switching from sine to cosine is just basically shifting or interchanging where the nodes are to where antinodes are. And then this is just shifting its starting point. So it doesn't really matter. I mean, you can use any trig functions you want. You can even use sine cosine or cosine sine. You can mix them up. It's no problem. But it's still a wave, but or still a standing wave. And so that's your wave function. And then I'm going to talk about the particle velocity. And so I need a time derivative. Derivative sine function is going to be a cosine. Train rule is going to give me an omega. So I get a omega sine kx. And then cosine omega t. And then the slope is going to give me a k cosine kx sine omega t. Right, so like in the particle velocity formula, basically this sine turns into a cosine. In the slope formula, this sine turns into a cosine. And when you look at these, they're no longer the same. There's sort of an offset in the location where this sine function will reach 1 is going to actually be where the cosine function is equal to 0, right? So there's an offset, and so like they sort of interchange where these are maximums, or these are going to be zeros, and where these are zeros, that's where these will have maximums. And then the same thing with the time dependence. They sort of are out of sync with each other because of this, right? Now, let's talk about the energy. So I'd be like an integral. And again, like the limits I choose are going to be up to what I need to be doing, but I have to take 1/2 the tension, and then times the particle speed squared. So I got a squared omega squared sine squared kx cosine squared omega t. And then I got the other term, the linear density. Oh, darn it! I got these switched around. Let me go back in here with my eraser. This is supposed to be the potential, or the kinetic energy. So that should be the mu, and this second term is going to be the potential. So that should have the k, or I'm sorry, the f, the tension, and of course the k here, k squared. But now we have cosine squared kx and sine squared omega t. And all right, so I want to point a couple things out. So one thing I can do, yeah, well, I mean, one thing you can do for sure, right, is like you can notice that these things in front, this thing in front here, and this thing in front here, they are actually the same. Even though they look different, they're the same. The mu omega squared and the f k squared are exactly the same because of the relationship between the wave speed, the linear density and tension, and also the relationship between omega k and the wave speed. So those are exactly the same. I could choose to use right one or as the other. I can choose to use either one. I can use either expression to represent these. And so if I choose, maybe let me choose this one to represent them both. Then I can write f, a squared k squared here, right? Let me just write this aside. So f a squared k squared is just equal to mu a squared mu squared. Again, that's true. And so in a sense, let's say I choose to use that one, I'll write to 1/2 f a squared k squared. And then I put the integral here. So I'm sort of factoring it out of the two terms. And then I have sine squared kx cosine squared omega t. What happened? I dated it somehow. That's weird. Okay. Omega t. And then I got the other one is cosine squared kx. Sine squared omega t. So that's the same, it's the same expression using the fact that those two things are the same. You can make that, you can interchange one for the other or whatever. So I decided to go this way, assuming that I maybe know the wavelength and I know the tension. So that's a little easier to work with. Now I have this to do. And okay, so that ain't too bad. Let's say I go over one wavelength again. For a standing wave, one wavelength would be like this. Right, so the standing wave, kind of oscillates like this between here and here. So this is one wavelength. So it'd be like that. If you're talking about, I always forget, I keep forgetting to mention like about harmonics and standing wave, like the sequence and stuff. And I think I'll get to that in sound more. But the idea is like this would be like the second harmonic. There's two antinodes between the one point and the other. And so if I went over one wavelength, like I'm talking about how much total energy there is in the second harmonic. If I just wanted one of these, I would just go over half a wavelength, and that'd be how much energy there is in a, so it would look differently. But some of you probably know this because you read the book and stuff, and I haven't covered it. But if you haven't read the book and you just wait for me to cover things, I sort of went out of order here a little bit. But let's just take, okay, well, there's got to be a limit. So I'll say one wavelength. So that's kind of the picture. What I'm looking at is like two of the two antinodes, from one node and to two nodes over. That's one wavelength. Right. Now you can see, okay, well, the same thing's going to happen. If I integrate the sine squared function over here and the cosine squared function over here, they're both going to give me the same thing. Because sine squared and cosine squared, their average value is 1/2. And so if you integrate over, a wavelength or whatever, you're going to get 1/2 of the wavelength. And so what I get is 1/2 f a squared k squared. And I get 1/2 of a wavelength. But then what's kind of left, and so that actually this term and this term are going to have to be the same thing when I do the integral. With the integral, whatever, they both become this, but I could kind of factor it out, and then what I'm left with is cosine squared omega t plus sine squared omega t. But of course, there's that trig identity, right? The best trig identity of them all that says cosine squared plus sine squared equals 1, right? That's my favorite one. And so what happens is the time dependence at this point just disappears, and so the total energy is 1/2 the tension times the amplitude squared times k squared, and I could write this as pi over lambda, or pi over k rather is what it would be. K may be convenient, lambda may be convenient. Either way, k and lambda are sort of interchangeable from the relationship k equals 2 pi over lambda. Yeah. So anyway, so it's kind of neat, because the answer doesn't depend on time, but of course it shouldn't depend on time, right? Because energy is supposed to be conserved. It's like a mechanical system, and the thing just oscillates like forever. So whatever energy it has should be conserved. It's not, there's no dissipation. We're not taking into account dispersion and things like this or energy would dissipate. Whereas it was supposed to be an ideal model, so energy should be totally conserved, and so the energy should not depend on time. Now, another way to actually do this is to actually go back to this step here and say, like the idea is take this step and say, look, I know energy is conserved, so why don't I just evaluate this integral, whatever, at a specific time. And then whatever I get at a specific time will be the answer because it's conserved for all times. And so if you can, for example, you could say, let's just set t equal to 0. Well, at t equals 0, the sine squared term will just be 0. And so this term's completely wiped out. And I just do this integral. And what'll end up happening is I'll get the same answer. Yeah, or you could say, well, let's choose the time where, omega t is equal to pi. When omega t is equal to pi, the cosine term is equal to 0. So this kind of gets wiped out. And this becomes 1, And so what happens is you get this, you just have to do the one integral. Of course, it ain't that hard to do it the way I did it. And it's kind of neat to see how the time actually disappears, even if you're not doing it at a specific time. So to see that it actually does hold at all times. But you could, as a shortcut, just choose to evaluate the total energy at a specific time, with the understanding, of course, that whatever result you get is valid for all times because of the conservation of energy. Okay. All right. So let me. I want to show you the other flash demo that shows the standing wave, and this one I think is really the coolest one. All right, so here it is. Here's the first. Again, it's the same like 4 graphs. The first graph represents particle displacement, and you can see that the string's oscillating up and down, but there's nodes and there's antinodes. There's points of antinodes where it goes up and down the most, and there's nodes where there's just never any displacement at all. And again, these 4 graphs are the same. And one thing you can see about the graphs is that they're definitely out of sync, right? The potential and the kinetic are out of sync. When the potential goes to 0, the kinetic goes up to max, and vice versa. When the kinetic goes to 0, that's when the potential's at max. So they're out of sync. And then the other thing, you can see that they're spatially out of sync. Where the potential is reaching its maximums, that's where the kinetic is always 0. And where the kinetic is reaching its maximums, that's where the potential is always 0, right? That's the whole thing I showed you with the functions, how the sine and cosines get kind of mixed up between the two. They're opposite on the time part, and they're opposite on the spatial part. You can see that right here. Now look at the string. The string is neat because it's not always purple, right? There's sometimes it's all red, and there's sometimes it's all blue, and there's also sometimes that there's some purple in there. And the idea is that I got this functionality. I can pause it and step it forward and stuff. So, well, I'll step it forward till we get to this point. At this point, this is like a turning point. That's when you have the maximum displacement at the antinodes, and it's just about to turn around and start going the other way. At this time, you can see that the potential energy is maximized. The kinetic energy everywhere is 0, right? Because it's like a turning point. Everything is stopped. And then you can also see where the potential energy is located. It's located at the nodes, right? There's no energy here at this antinode, but there is energy here at the node. There's no energy at this antinode, but there's a bunch of energy here at this node. And the reason there's a lot of energy at the node is because you can kind of see from adjacent pieces of string that's where they're mostly stretched from each other. Over here, there's no stretch between them. And so that's why there's no energy here, but there's all the energy here. And the total energy is just the same as the potential because the kinetic's not contributing. Now let's go forward a couple steps to the point where there's 0 displacement everywhere. So now, since there's 0 displacement everywhere, the string is not stretched whatsoever. And so therefore, there's no potential energy anywhere. However, this point right here, if you think about where it came from, that's this little particle string that was at the antinode positive side and is moving towards the antinode. It's at the antinode, but it's moving towards the negative side. And as it's moving through 0 here, it must be moving as fast as it will be moving. And so that's where you have like a maximum kinetic energy. And but then again, at these nodes, right, the particles never move. And so you always have 0 at these nodes, right? And so you can kind of step forward. There's an interesting point in time right here. This is like, I think, like 45 degrees, it's like a quarter cycle or something like that. And you kind of look at the thing, you can see that, it's kind of blue and red. It's got a mixture of each. There's more red at the antinodes. There's more blue at the nodes, but like the points in between are basically purple. The point directly in between them is purple. And you can kind of look at the functions, and they're basically, they both look like the same thing. They're just out of sync. And at this point in time, the total energy adds up to a constant everywhere. So it doesn't depend whether it's kinetic or potential. The sum of the two are the same everywhere. Just a second, Miss Jessica or Nikki, I'm in the middle of a lecture. Okay, there's like people watching me. Sonic. All right, I got to give her the tech so she'll be quiet, but apparently she don't know how to spell yet. All right, I know, I'm a horrible father. Should be having her read books. All right, all right, so let me just play it for a little while just so you see how cool it looks. Yeah, so anyway, so that's like the visual interpretation of all that physics books. Yeah, right. She can't read. Yeah, sort of visual interpretation of all that math we looked at a minute ago. All right. So again, these are available on the website. You just need to get a flash player. And I guess I was reading last night because I was like worried about the whole thing. I guess at the end of 2020, at the end of this year, by the end of this year, if not already, there's going to be no support for Flash on anything. So I really, this is coming to the end of these things. Yeah. So I'm trying to learn how to do this HTML5. Like you use HTML5 plus Java script, and you can, they say you can do almost the same stuff with this. But anyway, they say about old dogs and everything. It's hard to learn new tricks. So, but I'm gonna try to figure it out. All right. All right. Let me go back to the whiteboard or the notepad. Where is it? All right. Okay, so I think more or less with these notes, you'll be in a position to do those problems, like problems 2 and 3 on that set. There is a problem. I think it's problem 4 or something like that, where they talk about there's like 2 waves or 2 strings joined together, and there's like sort of a standing wave on each one, and it has a certain number of antinodes. It would have really been nice to talk about how standing waves could sort of fit between boundaries, but you can kind of look in the book for that, and those questions are not all that hard. It's just a matter of like manipulating the K and the omega and the V and the T and the mu and all that stuff together. And it's one of these kind of ratio problems where you write the relationships twice, once for the left side of the screen, once for the right hand side of the screen, and the 2 strings, and then you realize that they have the same tension, and so using that you can kind of eliminate some things, and next thing you know, you get your answer. It's not that bad of a problem, but yeah, I will talk about standing waves and like between boundaries and stuff like that when we get to in sound. I think we do standing waves in pipes at some point, so I'll talk about it more in that area. But anyway, I want to move on now, and I know we only got 12 minutes. I really am pushing things. I may end up having to add a day to the schedule, or to basically push everything back a day on the schedule. I'll let you know more about that. It might postpone the exam maybe, but either way, it'll still be a take-home thing where you have a week to work on it. Anyway, so let me kind of move on to sound. Right. So basically, that's the end of the mechanical. I think I've covered more or less all the topics in mechanical waves. All right, so sound. So sound waves are longitudinal. We can think of longitudinal waves. We can think of like sound pulses and things like that, but for the most part, even like a pulse of sound, it's usually at least somewhat harmonic in nature. Yeah, because like even like a pulse of sound will have a tendency to sort of repeat itself as it propagates, and so it'll have some harmonic properties. It may not be a continuous wave, but it'll be more or less like sort of it'll be like a packet of harmonic waves that sort of add together to form a sort of finite pulse of some sort. But within the pulse, there's oscillations, and those oscillations could be seen as you know, like a harmonic wave. And so we'll, you know, we're going to focus on harmonic waves, on like harmonic continuous waves. Or sound waves. And so you can say like Sx of x and t, because remember they're longitudinal, so the displacement is going to be going forward and backwards. And you know, I could write just a, this will go with cosine, kx minus omega t. So it's a traveling harmonic sound wave. And you know, so if I'm using Sx, if I do an axis here, so the x-axis, and kind of imagine maybe like a tube, you can, this is x equals 0. So the idea is that you can kind of imagine, we just draw like 3 dots. At a few different locations. Oops. What's going on here? This little button on the side of the pen is kind of sensitive. What is going on? All right, that should be enough. A little too much. All right, I got it. 1, 2, 3, 4, 5, 6. I want to do 7. So there's a middle one. All right, so let's say this is like lambda here. And so what is it, you know, so this is cosine kx. So the idea is that this is at say t equals 0. And so what you would see is that these particles are shifted forward to like right here. And that distance they're shifted forward is a, right? And then at this point right here, these are not shifted at all. Or, I'm sorry, that's not true. If this is a cosine function, right? Cosine is, so you imagine a cosine function. Let me make a graph of the cosine function underneath here. So this cosine function would be like this. It goes back up to here. Yeah, so these all at this location, they're shifted back like a negative amount by a. I want them all to be the same, but whatever. And these one over here are shifted forward by that amount a. And then like, I didn't draw these, but this would should be shifted up, you know, forward a little bit. And these would be shifted, or backwards a little bit. These would be shifted forward a little bit. And like, right, the particles that are right here would be shifted not at all. This would be shifted forward a little bit. These would be shifted backwards a little bit. And the ones right at the middle are not shifted at all. And so in a sense, there's these points where there's no shifting, right in here and no here. And you might think, well, they're just the same, but they're not, because in this location, you have like an extra concentration of air molecules, because the air molecules are kind of push forward here and push backwards here. And so this is what they call a compression. And these points right here, where they're shifted forward to the right of it and shifted, you know, backwards to the left of it, they call this point a rarefaction. And then the idea is that, you know, so this is exactly at t equals 0. As t goes forward, it's like this whole pattern just sort of shifts to the right. And of course, the particles themselves, the way it occurs is that the particle that is shifted here, as it goes to the right, it ends up just kind of moving back to where it started. And as the wave moves to the right more, it starts going, you know, backwards. As this moves to the right where it was started, I suppose it becomes a rarefaction, because the ones to the right of it are still shifted forward a bit, or, you know, they get shifted more. And then like this point right here is as the wave goes by, this little particle right here ends up shifting back and back more close to the start where it was, while the one, like the particle that's right here, shifts back to where to its natural position. Then it starts shifting forward a little bit. And so at the instant when this has zero displacement, this one is shifted forward a little bit. And this one, if you kind of follow through, you can see it will be actually shifted backwards a little bit again. And so this point right here would be a compression. And so, so the idea is that these you get the successive compression, high pressure zone and low pressure zones that are kind of moving across. And the high pressure, the compression and rarefaction points are always out of sync, like spatially, with where there's points of maximum particle displacement, right? So it's kind of interesting. It's completely different sort of interpretation. Like in a traveling wave, I mean, this point and this point, you kind of think of being more or less the same. I'm sorry, the transverse wave, you can kind of think of this point and this point being more or less the same. Let's shift it up a little bit. They're just the points where the thing's crossing through zero. But with the sound wave here, they actually have a slight, completely different sort of behavior. One is where there's like a high pressure and high particle density, and the other one is where there's low pressure, low particle density. Right. It's sort of a like kind of important like sort of difference. And then when you hear about sound waves, you always talk about compressions and rarefactions and stuff like that. All right, so now the thing is drawing a like a wave function for a sound wave, trying to draw it like this is crazy, right? Because all these dots and arrows and stuff, it's like really hard to do. And so the bit, what often we do is even though we're talking about a sound wave, we could actually draw the wave function as if it were a transverse wave, like a wave on a string. But the idea is that you recognize is that these points here where you have peaks, those are just where there's maximum particle displacement. This is particle displacement forward. This is particle displacement backwards, and again forward. And then these points where it crosses through zero are either compression or rarefaction points, I guess depending on the slope. Where it has a negative slope, it's a compression, whereas a positive slope, it's a rarefaction. For any harmonic wave, does it matter if you use cosine or sine? No, it really doesn't, right? The whole difference between sine and cosine is a phase shift of pi over 2, right? If you shift a cosine function by 45 degrees or by 90 degrees, it becomes a sine function and vice versa. I don't know if I said that right, but yeah, cosine would turn into a sine if you shift it by 90 degrees and vice versa. And so you really, by using sine or cosine, you can use them sort of interchangeably. The only thing you're really changing is like kind of maybe like your starting point or like its distribution or the location. If it's a traveling or a standing wave, by switching from sine to cosine, you're at least in the kx part, the term with the kx in it, you're exchanging where the nodes are with antinodes, where the antinodes will be. You're kind of exchanging those positions. And on the time part, if you kind of think of the switch on the time term, then you're just kind of, in a sense, just changing its initial, whether it's initially fully compressed or initially zero everywhere. So they really are completely interchangeable. You might think, well, is there like a conventional, way of doing it? And I've taught physics out of a lot of different textbooks, and some textbooks they consistently use cosine all the time, and some textbooks use sine all the time. So I don't even think there's like a convention. I think it's just up to the authors or preferences and stuff. And I don't know. So I kind of go back and forth. I don't really have an overall preference. I just kind of go back and forth depending on what I want to draw or whatever. I think if you're talking about like standing waves where there's a node at a specific location, if you want that location to be x equals 0, then it's nice to use a sine function because sine will be 0 at x equals 0 and stuff like that. And so sometimes there's some reasons to choose one or the other, but either way, yeah, they're totally interchangeable. Thanks for the question, Jimmy. A little aside there. All right, so that's kind of sound waves are. That's how harmonic sound wave, how the particles distribute. Now, you think about it. Actually, we'll learn later in this class. We're doing thermodynamics, and when we do that, we're going to realize that the air molecules don't just sit in place; they're constantly moving. And so, it's kind of funny to talk about the air molecules being displaced from their equilibrium position, because there really is no equilibrium position for air molecules. They're in constant motion. They're moving at hundreds of meters per second, just darting all around, bouncing off each other. They're going crazy. But the thing is, in a completely still air, even though the particles are moving really, really fast and all this, there's still basically a uniform distribution of pressure and particle density. And so what's really more important to think about is like actually the density. Like there could be a place where, they're all moving really randomly, but they just happen to be like more concentrated in one area, and an area maybe where there's less concentrated in that area. So there could be compression zones and rarefaction zones. And that's exactly what happens with sound. It's like they're all moving real fast, but their average position, their average is what is kind of oscillating like this picture. Does that make sense? It's really, kind of crazy. It's almost easier to picture sound waves if you kind of think of sound traveling in a metal. Like in a metal, you can kind of think of all the atoms in the metal as being like at these fixed locations in like a crystal lattice, right? And so the idea is when a sound wave goes through metal, those little atoms at their locations in their crystal lattice, they can vibrate, forward and backwards, but they're pretty much stuck at their equilibrium position. And so a lot of times I think when you're picturing a sound wave, you should maybe kind of picture a whole bunch of atoms like in a crystal lattice who are undergoing a propagation of a disturbance through that lattice. But what's in sound waves is kind of it's kind of harder to picture because the air molecules are really just randomly flying around, but there still is this distribution of pressure. And so a lot of times we talk about sound waves in terms of pressure. So let me talk about that. There's a pressure deviation. I think in physics 4A, you learn about pressure. Although it's in the thermodynamics question, or the thermodynamics chapter. And I know that unfortunately sometimes teachers don't have a lot of time to get to that because there's a lot of topics in 4A, and that's one of the ones at the end. So you might want to review, or at least kind of figure out what the definition of pressure is, like look in the textbook and read a little bit about that. But the pressure is like force per unit area. And the idea is that if you take like when we talk about air pressure, you can imagine taking an imaginary, square centimeter area. And you can think of like the air on one side, how hard is that pushing on that square centimeter? And then you take that force divided by a square centimeter, and that gives you the pressure at that location. And if there's an equilibrium, then, there'd be the same pressure on the opposite side too, pushing at it, And the thing about pressure is it's always perpendicular to the surface. So like if you talk about air pressure and you put like a surface that's horizontal or something like this, there's air pressure pushing down. If I turn the thing like this, well, now the air pressure is pushing this way. The air pressure is always perpendicular to the surface. But but it's not exactly like a force, like it's a vector quantity. Pressure is not doesn't have really an associated direction. It's just you can have the pressure of the air at some location in space, even if there's no area that it's pushing against, right? And so so there's no really associated air direction with it. So it's not really a vector quantity. But so the pressure deviation. So the idea is that there's an ambient pressure. We're totally out of time. Let's call this P0. And then the deviation is delta P. And in a sound wave, delta P could be written like this: delta P max, something like this. And I could say sine kx minus omega t. This is a harmonic continuous, And so the idea is that I could actually talk about a wave function for sound. I could actually put it not in terms of particle displacement, but I could turn it in terms, I could put it in terms of pressure deviation. And you can kind of see like in the picture up here, like if the particle displacement goes like a cosine function, like you can see, with the stuff up here, you can actually see that like in this situation, there's a sine function, right? And this is the pressure deviation. This is delta P, right? Because you have high pressure at the compression zone. You have low pressure at the rarefaction, and there's like 0 pressure deviation at this location. Even though there's a lot of displacement of air molecules in that location, they're all displaced the same amount, so they're not like really crushed together or pulled apart. You know, so it's not really a compression or a rarefaction. And so what happens is you can put it in terms of pressure deviation. You can put the wave function in terms of pressure deviation, but it ends up being out of sync with the with the displacement. Like I did displacement wave function. If you look at it in terms of displacement, yeah, this is displacement. All right, so yeah, we are a little out of time. We're a little 5 minutes over, and you know, this is really just an introduction, I guess, in a way. I want to talk more about this next time. So on Monday, we'll get to this. And on Monday also, we're going to start talking about the energy in a sound wave, and we'll talk about how you quantify that in terms of what they call intensity. It's just kind of a nice, a better thing to use for sound. So anyhow, that's it. If you got lab and you want to come by lab, you have some questions. I do have the, I'm going to actually stop recording this because it's different class stuff. Yeah, stop this and stop recording.